To start off, a brief history on atomic theory. So, back in ancient Greece, there was this guy named Democritus, and he came up with this idea that all matter, which is anything that has mass and takes up space, consisted of these particles called atoms, atomos, and eventually the idea just kept getting played with and played with and played with, and eventually we reached this idea, or Dalton reached his atomic theory consisting of 4 major points. So point 1 is that elements are composed of small particles, atoms. So any element, hydrogen, oxygen, carbon, sulfur, phosphorus, whatever, contains atoms. Number 2, all atoms of a given element are identical. So 2 oxygen atoms are going to look the exact same, 2 hydrogen atoms are going to look the exact same, but an oxygen and a hydrogen atom won't. So as we get deeper into the class, we'll understand about protons, neutrons, and electrons, how those work, and why these things are identical. Number 3, compounds contain atoms from multiple elements and they always have the same ratio. So water, for example, is H2O. So every single water compound molecule in the entire world is H2O. There's no difference. If you add another O, it becomes H2O2, hydrogen peroxide. If you add H3O, it gets a positive charge. It's called hydronium. There's all these different things, but H2O is always going to be water. No matter what, they're always going to be the same ratio. And then chemical reactions only combine, separate, or rearrange atoms. So this is pretty much saying that if we have a reaction going on, there's no actual creation or destruction of matter that's going to be occurring. It's only going to be changing electrons around, changing atoms around, moving them, separating them, combining them, but you will never, ever, ever create or destroy matter. This is actually called the law of conservation of mass. This is very important in chemistry. It states that matter cannot be created or destroyed. Matter cannot be created or destroyed, only transferred, as we can see with these chemical reactions. So, with this in mind, we kind of have a basic idea of what actual atoms are, what they kind of, their properties, right? So, all of these atoms are going to have different properties that go along with them, different chemical properties, different physical properties, as we talked about in the last video. The reactions of these atoms are going to be different. The compounds of these atoms are going to be different, and those all have different reactions and properties as well. So atomic theory is kind of the basis of chemistry, right? Understanding these atoms give us the ideas of why these things work the way they do, why they combine the way they do, why they react the way they do. So keeping this in mind is very, very important. Also, law of conservation of mass is a very, very important idea within all of chemistry. Sometimes you're going to be tempted just to make up matter or just delete matter in your test questions and your quiz questions. And it's always important to keep this in mind because it's not something you can do. It's not possible. You can only combine, separate, and rearrange these things to make them actually do something. All right, to kind of bring all these points together, I want to give you a little diagram that I think might be helpful. So let's say that we have molecule X, right? So we're just going to call it X. And those molecules, there's a bunch of little circles like this. They're just doing whatever they want, nothing really specific. And then we have molecule Y. And that's here. They're doing their own thing as well. So, molecule X and Y are 2 different atoms, but all of the molecules of X are identical, all of the molecules of Y are identical, but X is not identical to Y. So, X and Y have 2 different unique properties that make them unique atoms. We could say this one's hydrogen, this one's oxygen, we could say whatever, but for this example, X and Y. Now, if we want to make a compound of these atoms, we'll have compound XY, and for this sake, we'll just say it has one of each. So there's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So there's 7 of each. So we can have 1, 2, 3, 4, 5, 6, 7. And we'll attach those to 7 of the y's. Now we have 7 xy's. So chemical reactions can only combine, separate, or rearrange atoms. If I were to throw an extra y in here, that would be incorrect. We can't make matter. We also can't do this and just destroy matter. It doesn't work. We'd have to have an extra y right there. So it's important to keep these things all in mind. Hopefully this diagram gives you a bit more of a better understanding, something more tangible to understand atomic theory. So over time, taking Dalton's atomic theory, which was kind of the best thing that they had at the time, scientists decided to take these things and take them a step further. So one famous scientist, Joseph Proust, who's French, he actually took Dalton's third theory, compounds contain atoms from multiple elements and they have the same ratio, and took his own little take on it. He created the law of definite proportions and the law of multiple proportions. So whenever this happened, the law of definite proportions pretty much states that all compounds have the same amount of mass. It's pretty much like all carbon, like let's say we have a water molecule and a water molecule, they're gonna have the exact same mass. There's a definite mass, definite proportion of hydrogen, of oxygen that give us the same mass every single time. And secondly, the law of multiple proportions. So this kind of just states that, like, for example, if we have carbon monoxide, which is just CO, and then CO2, which is carbon dioxide, carbon monoxide is a 1-to-1 ratio of carbon and oxygen, which gives us 1. In this case, carbon dioxide, we have 1 carbon for every 2 oxygens, which gives us a 0.5 ratio of carbon and oxygen. It just pretty much states that every compound has its own ratio that we can use. That's just to make things easier. But these things are, like I said, they came from Dalton's atomic theory and their laws, so we know that they are in fact true. So taking Dalton's atomic theory and taking it to the next step, we have a definition of an atom that is the basic unit of an element that can combine. So atoms are the most basic things that we can actually put into chemical reactions that allow us to, combine matter, to separate matter, to react it, but not to create or destroy, because like we said earlier, law of conservation of mass, no creation or destruction of matter. So within atoms, there's 3 different parts: a proton, a neutron, and an electron. So these 2 parts up here, the proton and neutron, make up what is called the nucleus of an atom, and the electron makes up what we call the electron cloud. So further, protons have a positive charge, neutrons have a neutral charge, and electrons have a negative charge. So one important thing to understand about these 3 things, or about an atom, is that an atom will always have a neutral charge, no matter what. It will never have a positive or a negative charge. So the idea with this, to kind of break it down, if we have a +1, right, and a -1, that's going to equal 0. If we have a +2 and a -1, that's going to be a +1 charge. So we want every single atom to have that 0 so that they're equal, not this, because a charge, or a positive or a negative, is going to be called what is called an ion, something completely different. So to make sure we have this down pat, I want to talk about these things called atomic numbers. So on the periodic table, you're going to have an element. For example, let's say it's carbon, right? It's going to have 12.01 down here, a 6 up here, and that's it. Maybe it'll have carbon, but whatever, it's C. So this 6 is what we call the atomic number. And the 6 directly correlates to the number of protons we have. So one atom of carbon contains 6 protons and 6 electrons to make it that 0 to 0. Neutrons have no effect. We'll get into isotopes, things that have different number of neutrons in a second, but I want you to understand this concept. Every single atom of carbon will have 6 protons and 6 electrons every single time. Same thing with oxygen. Let's go to oxygen now. So let's say we have an O, it's going to be atomic number 8, and it's going to be 16 below it. We're going to have, for every oxygen atom, we're going to have 8 protons and 8 electrons. Every single time. Every oxygen atom will have the exact same number of protons, exact same number of electrons, making it that 0 because we have 8 and 8. That cancels out, giving us that 0 at the end. No charge, like that. Same thing with carbon, 6 protons, 6 electrons. The positives and negatives cancel out, giving us that 0. Every single time, it's going to be neutral. So over the history of atomic theory, atomic structure, there have been countless different structures that we have taken into consideration for what an atom looks like. One of the first major ones was actually by this guy named J.J. Thomson, and it was called the plum pudding model. So the idea was that you had the singular circle, and it was a positive charge, so we'll put a positive, and that you had all of these electrons within it, looking kind of like a plum pudding, a chocolate chip cookie, whatever you want to call it. But there was obviously, so we have 1, 2, 3, 4, 5, 6. So we also need 6 protons just to match, to give us that 0, neutral charge. But it would look something like this. Now obviously you might be saying, where are the neutrons? This wasn't really even a thing that they knew about at the time, but the plum pudding model was a very, very important, not discovery, but theory that came about by J.J. Thomson. The next notable atomic theory that has come up, or structure that's come up, was by this guy named Ernest Rutherford. And he actually came up with the idea that atoms pretty much had this central nucleus and they had this electron cloud on the outside. And this electron cloud is pretty much all empty space, but there was a nucleus. So his experiment was what's known as the gold foil cathode ray tube experiment. And pretty much the idea was that there was this piece of foil that he shot a beam through, and there was like a wall, like kind of curving around, and the electrons would hit different things, showing that the wavelengths of the light would all go in different directions, but sometimes the light would shoot back. And this was pretty much saying that if the light were to make it to the wall, it would hit the electron cloud, but if it were to reflect back, it would have hit the nucleus, causing an opposite force that way. So this seemed pretty valid. For a while, it seemed like a pretty good idea for the atom, but after a while, people realized that the masses were off. We talked about those ratios before, and there was actually a huge debate between hydrogen and helium. So hydrogen is atomic number 1, and helium is atomic number 2. And like we talked about earlier, figuring out those protons and neutrons, hydrogen would have 1 proton, 1 electron. Helium would have 2 protons, 2 electrons. So they have the same ratio. They're all a 1-to-1 ratio. So something's off with them. Something needs to be different. Otherwise, they look like they're the exact same thing, just 2 hydrogens and 2 hydrogens together make a helium, which isn't the case. Because 2/2 is 1 and 1/1 is 1. So something had to be different with them. That is where we get the idea of neutrons. The neutrons add something to this nucleus, as we talked about earlier, giving it a bit more mass, something, changing this ratio a bit more, giving us different numbers for each atom. So when talking about these things, it actually came from this guy known as J.J. Chadwick. And he came up with the idea of neutrons. He kind of coined the term. He gave them, the light. He showed them to the world, and now they're such a widely accepted thing. We have these special compounds known as isotopes just because of neutrons. And yeah, but that's pretty much the history of atomic theory. That's kind of how we've gotten to where we are now. But let's get into a few examples, kind of talking about how to actually figure out what's in an atom on a more deep level than what we did before. So now on to a bit more of actually what is within atoms, how we can describe them with words, definitions, and how we can see them on the periodic table. So starting off, 2 things I want us to go over: atomic number and then mass number. 2 different things. They sound a bit similar, but they're not. Atomic number is going to be the number of protons, and then mass number is going to be number of protons and neutrons. So it's a bit backwards on this model, but atomic number is going to be Z, and mass number is going to be A. X is just the element. So for a certain element, let's do boron, for example. Boron is element number 5. So its atomic number is 5. So we could do boron, the 5 down here. And then let's say our mass number is 12. So now we know that our mass number is 12, our atomic number is 5. We can now do a bit of a calculation to figure out how many neutrons are in boron, in this specific atom of boron. So taking 12 minus 5, we get 7. So we know that we have, for boron, 5 protons because of our atomic number, 5 electrons because we have to have that equal charge, so it's always going to be 5 and 5. But our neutrons was something we couldn't figure out earlier. Now we could take our mass number, subtract it from our atomic number, and get our number of neutrons. So in this specific case of boron, we have 7 neutrons. And then there's these things called isotopes. Isotopes are atoms of a certain element, in this case boron, with different numbers of neutrons. So instead of a 12 here, let's say this is a 13. And then changing that to 13 minus 5, that equals 8. So as we can see, we have one higher number, meaning we have one more neutron, giving our boron atom just a bit more mass. we still have 5 protons, we still have 5 electrons, because we have to have that atomic number that's on the periodic table, and it has to be the overall neutral charge. And then we have to do our mass number minus our atomic number, giving us that 8. We could also do, maybe the specific case of boron has 11 of a mass number. So we would do 11 minus 5 from our atomic number, giving us 6. And in this specific case of boron, we would have 5 protons, 5 electrons, and 6 neutrons, giving us a different isotope. One last example. Let's say we have a mass number of 10. So 10 minus 5 gives us 5. So we would have 5 protons, 5 electrons, and 5 neutrons. And that's okay. It's just giving us different slight changes in mass to our boron atom. But at the end of the day, what makes it boron is this. The 5 protons will make it boron. Same thing with hydrogen. So hydrogen is your first element on the periodic table. It's your 1. 2 is going to be helium. At the end of the day, you can have as many neutrons as you want. You can have 1,000,000, you could have 0, you can have 20. Whatever. The 1 proton will always make this hydrogen. For the second one on the periodic table, helium, 2 protons will always make this helium. For number 5, boron, the 5 protons is what's going to make it boron. For carbon, 6, the 6 protons is always going to be what makes it carbon. The number of protons is the only thing that matters what element it is. The only difference is how much mass the specific, or how much weight the specific atom holds, and that comes down to the number of neutrons, as we could see with this mass number minus atomic number calculation. As we can see here, every single one of these examples was boron. It just had a different number of neutrons in it, making it either slightly heavier or slightly lighter. But like I said, this is very important. The number of protons is the only thing that will make a specific atom a specific atom. 1 hydrogen, 2 helium, 5 boron, 6 carbon, 8 oxygen, whatever you want to do. As long as you have that number of protons as seen in the periodic table, that is the only thing that makes the atom the atom. So one last thing before we kind of get on to the next topic is whenever we're talking about mass numbers, obviously all of these things kind of look very similar. You're not really talking about the neutrons as much in chemistry. It's a lot more of the electrons and protons, but we need a way to identify these things and make sure that they're different. So we have this thing called the mass number nomenclature method, and we take the mass number, so right here, all of these numbers, and we put it behind whatever element we're talking about, so in this case boron. So boron 12 for this one, boron 13 for this one, boron 11 for this one, and boron 10 for this one. So if we're looking at this, we could take our, we could just, like if we don't even have this up, we could take our boron 12, subtract it by the 5, we get 7, boron 11, take it from the 5, we get 6, as you can see here. But it's just another way that we can name these things. It's common more with things like uranium, whenever we're talking about like bomb making or radiation, whatever, like uranium-238, uranium-235, different types of masses that allow for different types of reactions, different types of properties, but it still is uranium at the end of the day. All right, before we end, I want to go through a few examples, make sure you guys understand this topic a bit more. And there's always going to be more practice problems down below. Click the link in the bio. There's always going to be some sort of practice problems you can go over, just to give you guys a bit more work for your tests and your quizzes. Starting off, number 1, we have 20/11 Na. So Na is sodium, and we know that looking at this, we could see this type of thing. We have 20 as our mass number and 11 as our atomic number. And we're trying to figure out, in this case, protons, electrons, and neutrons. So starting off, let's look at our atomic number, 11. Atomic number is number of protons, so we're going to have 11 protons. And since it's an atom, we have to also have 11 electrons because it has to have that overall neutral charge. Now, taking a look at our number of neutrons, we have our mass number, which is 20, and we'll subtract it from 11, giving us 9. So we'll have 9 neutrons in this case. So sodium on the periodic table is going to look something like this. I think it's like 22.99 or something like that, but I could be wrong. But it's 11. That's the main thing here. This 11 is the atomic number. So if you were given just this on your exam, you could do the exact same thing. You could figure out number of protons, number of electrons. You just need a mass number to figure out the number of neutrons. Number 2, we have an O with a mass number of 17. So if we take a look at our periodic table, oxygen is going to have 8 as its atomic number. So like we stated before, we could also just write it down here because we know that our atomic number is going to go right there. But 17 minus 8 gives us 9 again. So we're going to have 8 protons and 8 electrons because we need that atomic number and the overall neutral charge. And as we did from our mass minus our atomic numbers, we get 9, so we have 9 neutrons. So 8 protons, 8 electrons, 9 neutrons. Carbon 14. So this is going to look something like this. And looking at the periodic table, carbon is going to have an atomic number of 6. So we could throw our 6 down there. 14 minus 6 is going to give us 8. So we have 6 protons, 6 electrons. From our atomic number, has to be overall neutral charge. They have to cancel out. And then 8 neutrons. So 6 protons, 6 electrons, 8 neutrons in carbon 14. And then lastly, 22 over 11 Na. So sodium again, going back to this one. Our atomic number is 11, so we have 11 protons, 11 electrons, and then 22 minus 11 is going to be 11. So we're also going to have 11 neutrons. And as we can see, the differences between these two, in this case we have 11 neutrons, in this case we have 9. They're both sodium, but this one's just a little bit heavier, has a little bit more neutron, so it's an isotope. This would be sodium 22, this would be sodium 20, to the exact same atom, but they're different isotopes. This is why it's important to understand the definitions, understand the actual parts of the atom, why these things come together, and overall how we can apply these basic equations into figuring out something so important.